So I'm Allison. First of all, thanks so much for having me. It was really fun to participate in this event. So my project is called Pass Analyzer. First, a little bit more about me. So I'm currently a software engineer. I work on the Google Chrome browser, but I'm also in a part-time data science master's program at the University of Washington, which is why I was really interested in participating. I've been a lifelong soccer fan ever since my elementary school PE teacher got drafted as a goalkeeper in the WUSA, which is the first professional league in the US. And a lifelong player as well, though at the recreational level. And then outside of that, I'm definitely an avid hiker and backpacker. So all of my pictures are not headshots, they're pictures of me hiking somewhere. So my motivation of this project was to build a tool that could support analyzing the decision-making associated with passes made during a game. I wanted to both allow you to get a high-level understanding of what's happening over the course of a game, but also allow you to drill into specific passes, learn more about them. To do this, I built an interactive web application. So my background is primarily with web design. And the use case I was targeting was something that could supplement film sessions and allow you to answer some sort of questions like what timeframes had high pass completion rates for a specific team? Was a certain pass that a player made a good choice in that situation? What options did a player have when they made a pass? The development stack that I used for this, so it was an HTML web application. I used D3 to do the visualization of the passes, Bootstrap for a little bit of the formatting of the website. And then I used pass and likelihood data that I'd cleaned to CSVs. So this is all done offline to make it a more performant application. So I deployed it on App Engine, so it's actually available if you go to wisd.alisongale.com. Though it's not the most mobile-friendly site, I optimized it for desktop, but it is still usable on mobile. So now I'll do a little bit of a walkthrough. I did screenshots of the application because live demos are always challenging. So this is what it looks like. In the main center of the page is a visualization of a field with all the passes represented by arrows. Completed passes are marked in blue and incomplete ones are marked in red. I recognize that red and green are not great in terms of contrast, but hopefully you're able to see these. At the top of the screen, there's a drop down where you can select which match you want to drill into. So for example, if you wanted to look at Denmark versus Finland, you can select that and then select which individual team you wanted to look at. I did this because I didn't want to clutter it with too much information, and so I decided to focus on a single team at a time. Once you selected that, at the bottom of the page is a slider where you can see each see 5-minute intervals of passes. And as you move the slider across the screen, it'll show you how the passes change over the course of the game. And so to sort of simulate that, for example, now if you slide to this 15th to 19th minute, you'll see that Finland has a lot of possession. They're defending on the left side of the screen, attacking towards the right. And so here's an example where they're having a lot of possession, doing a lot of passes, but nothing's really breaking past into the attacking half of the field. The few attempts that they've had either to clear it from the back or to attack from center field were largely unsuccessful. And so as you scrape across, you can see time periods where they either have very little possession, a lot of possession, defensive versus attacking possession. Now it gets a little more fun when you actually click on a pass, and this is where you can drill into the details of it. So once you've selected one, I highlight it with sort of a dotted line. The attacking team is represented with blue dots. The defensive team is represented with yellow dots. This data comes from the 360 frames provided by StatsBomb, which gives you the positions of many of the players on the field. Note that not every player is represented. Some of them are off screen. And so unfortunately, you're unable to get those positions. But it does usually show a lot of the players in the direct vicinity of the ball. On the right, I highlight a bunch of details of the pass. Things like who made it, who the recipient was, the play pattern. So this was from a counterattack, the outcome, and then a likelihood, which is from a model that I'll describe in the second half of this talk, which assigns a likelihood of completion to the pass from the point it was made. In this example, this was a very low likelihood of completion, which is consistent with the fact that it was an incomplete pass. Additionally, I show the passing accuracy for the individual player who made the pass, and other information about, the height and body part used to make the pass. Here's an example of a completed pass. You can see that it's highlighted in blue, and the likelihood of completion associated with this one is 0.95, which makes sense given that it's a back pass, presumably to a defender on the player's own team. And it's a ground pass as well, which is, I ended up realizing was very highly associated with pass completions. All right, so now I'm going to dive a little deeper into the pass completion likelihood model, which is what took the bulk of the time after making this initial visualization. The first step for this was cleaning the data. The most important thing was to remove all sort of outcome-related variables from the data, except a single Boolean, which represents the response, which was whether it was completed or not. This is important because some of the data might have been things like whether there's an interception or something, which is not information that's available from the moment the ball was kicked. It's information that would be like directly correlated with whether it's a completion or not. And so I wanted the features of this model to be entirely things that were either available or could be extrapolated based on the moment the ball was kicked. There are also things like location differences between the 360 frames and the pass data. When I found those inconsistencies, I defaulted to using the 360 frames so that the location of the player making the pass is consistent relative to the other players that are rendered on the field, so you'll understand their position relative to the context of their teammates and opponents. And then the final step after cleaning the data was to apply a one-hot encoding for categorical variables. This was necessary for the models that I was building, and also allowed you to find the effects of individual things like whether it was a ground pass or not, whether the player was a defender or a forward or not. So here are a sample of some of the features I used as inputs, things like the position of the player making the pass, the location of the ball. So this is XY coordinates where it's around like each number is roughly the number of yards, but it's sort of normalized to the dimensions of a soccer field. Things like the pass angle and height as well. But in addition to the basic features that I got directly from StatsBomb, I also calculated some derived features. One of them was things like the nearby teammates and opponents, where I sort of built a cone around the trajectory of the pass and then calculated how many opponents and teammates were in that area. This was a way of sort of simplifying the 360 frame data into something that was easier to fit into the model and would give me a little more information than just the raw positions of all the players. That would be really lead to a very sparse data set and would be really hard to parse from the model's perspective. Also things like the number of passes in the current possession to see if that was useful. Overall, I analyzed 54,000 passes as part of the men's Euros. This was just an interesting visualization I came up with, highlighting the number of passes per 90 minutes relative to the completion ratio, which you can interestingly see has a positive correlation. I highlighted Italy and England in the middle. Those were the two teams in the final. They were kind of in the middle of the number of passes per 90 minutes, but quite high in the completion ratio. And so clearly that's very important to performing well in a tournament. The next step was feature selection. So there was a ton of data from StatsBomb, and I didn't want to just use all of it for all the models because it would slow down the process of building the models and also possibly lead to overfitting. And so I used feature importance from one of the models that I used to narrow down the final set of features. And so I focused on ones that were highly important to the model. So here are some of the sample values. You'll see that whether it was a ground pass or not was determined as probably the most important input in determining whether there's a completion. Also the pass angle. That's something where I assume a back pass is probably very highly likely to be a completion, whereas a forward pass, less so. Interestingly, whether a player was under pressure was not as important, but I presume that the players are very used to playing under pressure, so that's maybe not as much of a factor to them. And this step was really interesting to provide intuition about what was important. And also some features were also could be proxies for other things, like whether it was a cross or not was also not very important. But you could probably tell whether it was a cross or not based on the location of the pass and the angle. That's probably why that particular field wasn't as important. So now I'll highlight some of the models I considered. The first one I started with was the k-nearest neighbors. This is a highly nonlinear model, which was important because, I wasn't expecting that, like, as you move across the x-axis, that passes are more likely to get completed. There might be sort of idiosyncrasies about specific zones on the field. But this model doesn't do the best with like the particularly sparse data set, but it's very simple. So it's a good one to start with. On the right side, I show a confusion matrix of the complete and incomplete passes, both the true values and the predicted values. You can see here that while the model overall did pretty well, it was pretty poor at identifying incomplete passes. Less than half of them were correctly identified. And so in general, this is not a particularly useful model. The next one I did is I moved to the opposite end in terms of complexity to use a neural network. So neural networks use hidden layers to identify relationships between the features. This is a highly flexible model again, but the downside is it's a lot less interpretable than some other models. It's also quite slow to train, but the performance was much better than k-nearest neighbors. So it did correctly classify over 50% of the incomplete passes, which was really nice to see. And then the final one I used was gradient boosted decision trees. So decision trees in general are nice because they are very interpretable. They can, when a basic one is used, it directly tells you, if your X location is less than this or greater than this, and this variable is true, then classify it as a complete pass. And so it's really helpful for getting things like the feature importance. And then the gradient boosted decision trees, this is a modified model that reduce bias by incrementally building a large number of trees. And this actually ended up having the best test performance that I saw. So it correctly classified almost 2,000 of the incomplete passes, which is a much better ratio than the other models I used. So after I looked at those three models, the next step was a bit of parameter tuning. So I used cross-validation to optimize the model parameters. I found that the default parameters actually were quite good. This parameter tuning step only moderately improved the test accuracy, but it's still important to validate and make sure that the parameters I was using make sense for the data. So this is a summary of the results that I saw. So I started actually with doing the gradient boosting decision tree with just the location as a feature, ignoring all of the other data sort of as a baseline. And found that the accuracy was around 0.83. The k-nearest neighbors was only marginally better than that. And then you'll see that the neural network and gradient boosting both were a significant improvement on that. Parameter tuning, only a slight improvement. But then once I had picked my model, picked all my parameters, and was ready to deploy this into my application, I built the model on all of my data. And so while it's not a test accuracy, but the accuracy of that model for the end deployed version was 90%, which was pretty nice to see. So what are the next steps after I built this model, built this web application? And one of the things I was really curious about was how generalizable is this model? Does it work if I provide it a different data set? So I actually took data from the FAWSL 2020 to 2021 season. This is a women's club season that was like the first post-COVID season compared to a men's international tournament. And I found that the test accuracy was not great, but not awful. And only 50% of the incomplete passes were made. So it shows that, and also for this data, they don't have the 360 frames available, which reduces the accuracy of the model a bit. And so in general, the model is like somewhat robust in that it's not awful with this data, but it definitely probably would perform better if I was training it on a more similar data set. Presumably if I built it on a previous FAWSL season, and then it would have much better performance. Some additional ideas if I were to expand this project and continue working on it or had more time. Now that I have this model, I could suggest alternative passes that have higher completion likelihood. maybe tweaking the angle of the pass, maybe tweaking, what body part you use to make the pass, the height of the pass, to suggest alternatives. Another thing that would be really fun is to identify player and team effects on the likelihood. This would be easier on a larger data set. For this tournament, some teams only played 3 matches. And so you might not have enough data to identify those player effects. But if you had maybe a full club season, that would definitely be an interesting thing to explore. And then finally, it would be awesome to build a model to quantify how much a pass increased the likelihood of scoring, because certain times in a game you do want to play for possession, but other times you might want to make a risky pass that's not likely to be completed because it's going to put you in a really good position to score. And so if you could quantify how much a pass increased the likelihood of scoring, then you could combine that with a model that shows the likelihood of completion. And you would either want a pass to increase your likelihood of scoring, or I guess conversely, decrease the opponent's likelihood of scoring, or have a high completion likelihood, maintain your possession while you work to find that pass that's going to increase your likelihood of scoring. And so if you had those two together, then that would really give you a good idea of the true value of a pass. So I have some links for this project. So it's currently hosted on GitHub. Again, you can visit it at wisd.alisongale.com. And you can follow me on Twitter at ALG137. Thank you. All right, now does anyone have any questions? How does this work? Yes. Oh, I think there's microphones coming.
So, I mean, first, hi, everyone. This is Mona. And the interest, like, I really like the aspect of all these, technical parts, because I just joined sport field for 6 months, and I really love to bring like machine learning and all those stuff into this. So it was very interesting to me. I have a question. At the beginning of the slides, you said you took out some of the variables that had effect on the outcome. So it was in the fewer beginning of the slides. I would like to know more about what was the variables you took out, and what was the reason exactly? What will you see if they were in? What was the difference?
So it was mostly things like, some of the data coming from StatBomb were like the recipient of the pass. And so if there is a recipient, it was a completion. And so that's not really learning anything. And so what I wanted was to analyze the decision-making of the player at the moment the ball was kicked. And so any variable that could have been influenced by anything that happened after the ball was kicked, I wanted to get rid of. So I think there might have been variables about whether there was like a deflection, whether there was an interception, who received the ball, other things like that, because that was something that you couldn't have taken into account at the moment the ball was kicked. And so when the moment the ball was kicked, you knew the direction they were kicking it, you knew like how high the ball was going to go based on the velocity when they kicked it. You knew their location on the field, you knew where everyone was at the moment it was kicked. But there are things like you don't know where a player was the moment they received it, because you don't know where they're going to run necessarily. It's possible to make the run that you expected them to make, but it's possible they're going to run in a different direction. And so I didn't want anything that would like sort of make the model perform like, because if I included the recipient, then anytime the recipient was null, then you would know for a fact that it wasn't incomplete. And so then the model wouldn't be particularly interesting. Yep.
Hi, I'm interested in the where you analyze the nearest teammates and nearest opponents. How did you what was the criteria that you used to categorize those as being near to the particular player?
Yeah, that's a great question. So I calculated, it was all based on angles. I forget the exact cutoff I used, but I picked a specific, I think it was in radians. So I picked like a specific, like plus or minus this many degrees, and then kind of just extrapolated it out. And because of the 360 frames, like they only sort of have players kind of nearby to begin with. And so I just kind of extrapolated in general. And so I just basically took the position of the player with the ball, the person they were passing to. I had to remember my trigonometry from high school, and yeah, calculated the angle from the passer to each of the players on the field. And if it was within this plus or minus of the actual pass angle of some buffer, then I included them as like being nearby. So it's possible some of them were like way past the ball when it was received. It's possible some of them were like directly in front of the player. But that's generally the process I used. Yeah, so I use the angle because presumably if someone is close to you, then when you use the angle like that, if someone's really far away from you, if they're 60 yards away, presumably they could run pretty far to receive the ball. And so I wanted to capture players in a relatively large chunk of the field. Whereas if a player's really close to you, they're not going to be able to move very far to receive the ball. And so they're only going to be relevant in the play if they're relatively close to that cone. Yep.
Hi. I'm here if you can.
Okay.
My name is Robin. So I did actually a pretty similar project for the Big Data Cup that I'll probably bug you about afterwards in hockey. So I guess my question was kind of similar to hers with the angle. So you're taking it as a known whether it's in the air or on the ground, right?
So
One
for this, I didn't take into account the height at all of the ball. It was all just based on the it was all based on the angle in the XY grid and nothing in the Z axis.
Yeah, but one of your variables was if it's a ground pass or not.
Yeah. Oh yeah. That was a completely separate variable.
Okay, yeah. So you could, I guess in theory, maybe extrapolate and say if it's a higher pass, would you maybe consider using a different like triangle system, like someone a couple feet in front of you on the ground isn't going to be able to get it. If you know it's in the air, you might want to consider like a different shape of who's going to be considered or a distance or something. Would you maybe change that and who is eligible to change to catch it if you know it's a ground versus if it is an in the air pass?
Yeah, definitely. Because yeah, when it's in the air, then kind of like nearby players, it could go over their heads, and so their positioning might not be as important, and presumably they're not going to receive it. Whereas yeah, if they're far away, then they would definitely be much more likely to receive the ball. So yeah, that's definitely a good idea to like tweak that encoding to like more accurately. And you could probably look at like historical instances of who actually does receive the ball and what type of pass is made to figure out what for a given trajectory, like maybe a back pass, you don't actually care about like anyone's position, because if it's a back pass, it's likely just going to your teammate that's behind you. Whereas if it's a ball that's going into the other team's attacking half, then you might actually want to make a really wide angle because players are often going to be running like 60 yards to get onto the end of a pass. So definitely that could be like modified to more accurately capture the different types of passes and who is likely to receive them.
Thank you so much, Allison. You're a D3 queen.